Every time you search on Google, it returns millions of results in a fraction of a second. But here's the real question. How does it know which pages to show first? The answer comes from an elegant branch of mathematics called graph theory. Let's start from the basics and build up to the exact algorithm Google uses. A graph has two building blocks. First, nodes, also called vertices. A node represents any object or entity. It could be a person, a city, a computer, or a web page. We draw nodes as circles or dots. Each node is a thing we care about. Second, edges, the connections between nodes. An edge represents a relationship. If two people are friends, we draw an edge between them. If two cities have a road, we connect them with an edge. Together, nodes and edges form a graph. That's all there is to it. Let's see graphs in the real world. Think about social networks like Facebook or LinkedIn. Every user is a node. When two people become friends or connections, an edge forms between them. Your entire social circle is a graph, with you at the center connected to everyone you know. Roadmaps are graphs too. Cities are nodes. Highways are edges. GPS navigation finds the shortest path through this graph. And the internet itself is a giant graph. Billions of web pages, each linking to others. Every hyperlink you click is an edge connecting two page nodes. Now, let's look at different types of graphs. In a directed graph, edges have direction. They're one-way streets. Think of Twitter. If you follow someone, that's a directed edge from you to them, but they might not follow you back. The arrow shows who follows whom. In contrast, undirected graphs have two-way edges. If there's an edge between Alice and Bob, you can travel in either direction. Facebook friendships work this way. If Alice is friends with Bob, then Bob is automatically friends with Alice. The relationship goes both ways. Edges can also have weights, numbers that measure the strength or cost of a connection. In a road network, the weight might be distance in miles. Between airports, it could be flight time. Weights let us ask, what's the shortest or cheapest path? Not just any path, but the best one. Here's a fundamental question in graph theory. Which node is the most important? Think about it. In a social network, who's the most influential person? In a transportation network, which station is most critical? This question is called centrality, and there are several ways to answer it. The simplest measure is degree centrality. It just counts how many edges connect to each node. More connections means more central. In a social network, the person who knows the most people has the highest degree. It's intuitive. The most connected node is often the most important. But connection count isn't everything. Betweenness centrality measures something different. How often does a node appear on the shortest path between other nodes? These are the bridges, the gatekeepers. They may not have the most connections, but they control the flow of information. Closeness centrality asks, how quickly can a node reach everyone else? It measures the average distance from one node to all others. A node in the center of the network can reach everyone in fewer steps. Think of it as being in the middle of the action, able to spread information quickly. Now we have the tools to understand Google's breakthrough. In 1998, Stanford students Larry Page and Sergey Brin faced a massive challenge. How do you rank billions of web pages? They realized the web is a giant directed graph, and they invented a new way to measure importance. Their key insight was this: a link from one page to another is like a vote. If page A links to page B, A is saying B has valuable content. The more votes a page receives, the more important it must be. But here's the clever twist that makes PageRank special. Not all votes are equal. A link from an important page counts more than a link from an obscure page. If the New York Times links to your blog, that's a stronger endorsement than a link from a random website. This creates a circular definition. Importance depends on who links to you, and their importance depends on who links to them. Here's an elegant way to think about it. Imagine a person randomly surfing the web forever, clicking links at random. At any given moment, where are they most likely to be? Pages with many incoming links from popular pages will be visited more often. The probability of being on a page becomes its PageRank score. In practice, PageRank is computed through iteration. Start by giving every page an equal score. Then, repeatedly update each page's score based on the scores of pages linking to it. Each iteration gets closer to the true values. After enough rounds, the scores stabilize and stop changing. That's the final PageRank. And that's graph theory, from simple nodes and edges to the algorithm that powers the world's largest search engine. These concepts appear everywhere: social networks, navigation, biology, recommendation systems. Understanding graphs helps us understand our connected world.